As promised, this slideshow is going to present what's known as the mixed design repeated measures ANOVA. And that is a design where not only you have the repeated measures as a factor, but within subjects factor. In other words, each subject is repeatedly measured, but you also have an independent variable that represents differences between groups. So it's mixed because you have both a between groups and a within groups factor. And so I'm just going to go over the purpose of basic repeated measures, and then we'll look at a mixed design. So your basic repeated measures just compares differences when populations are not independent from each other. In other words, a group or any individual in the data set is correlated with its individual value at level 1 of the repeated measure, level 2 of the repeated measure, level 3, etc. So the populations are linked by having repeated cases. We'd looked at ANOVA before when you had independent samples, when the samples were not related to each other. So this is kind of like a paired sample t-test in that each case is related to a case, which may be actually, usually it's the same individual at both points of measurement. T-test is limited to 2 measurements. Repeated measures can accompany or can treat multiple repeated measurements. And in the basic repeated measures, each subject is tested at all levels of the treatment factor. This is true for the mixed design, but what you have is you have subjects as well who are not dependent or not related to one another. So you have both dependent groups, a group, for instance, where all the people are correlated across multiple time points, and you have a different group or multiple different groups, again, where they are all correlated across their repeated measures, but they are not related or correlated with the other group or groups. So basic reasoning of basic repeated measures is to ask whether variations within these correlated individuals, when they're measured on the same dependent variable multiple times, is it attributable to that factor that is measured multiple times, or is it variability likely due to chance? So is it related to the time they are measured as opposed to chance? Is there dependent variable, say an outcome, related to the time of measurement, or is their outcome stable across time where any changes across time are essentially chance? And this is very useful when you're looking at growth over time. That's your essential use of growth over level of dose, decline over amount of exercise within a week, etc. So the repeated measures have assumptions. First of all, the observations between subjects are independent of one another. So while the repeated scores of case 1, for instance, are contingent on one another, a person's change over time has an element of being individually that person. The multiple cases are not related to each other. The populations are normally distributed on the dependent variable. So That is the assumption of the normal distribution, and it needs to be true for all levels of the factor. So you're looking for a normal distribution on time 1, time 2, and time 3. And that is difficult to test. SPSS offers no specific test of that. There are kind of multiple tests that you really need to combine descriptively to make a decision about normal distribution. Fortunately, the F-test or the tests in a mixed design model are fairly robust to violation of the assumption. It's something you need to look at mostly descriptively. Sphericity is that the variance of the variance, so this is not looking at the shape, but are looking at the breadth of the variation, are similar at level 1, level 2, and level 3. And if you have a between groups factor, which we'll see in the mixed model, then there's assumption of homogeneity of variance. So if you have one group that's measured over repeated times and another group that's also measured over repeated times, but those groups are independent, you're comparing the differences in their means over times, then that's a homogeneity of variance issue. So the advantages of the design are, first of all, that you can look at change over more time points than 2, that it is more powerful than, say, multiple t-tests. And therefore, because it's more powerful, it requires fewer subjects. So it often is an economical test. However, that's only true when it's the correct thing for a design. So when you have what's called a mixed design, which is what's new here, then you have multiple questions that can be asked, just as you would have in a factorial ANOVA. So you, first of all, can look at the typical question in a simple repeated measures ANOVA, whether this is the within subjects effects, and that is the same as before, is variation within individuals when they're measured on the same dependent variable multiple times. Is it attributable to that time variable or the dosage variable or whatever else you have as your repeated measure? So basically, is there change across the repeated measures that is not likely due to chance? If you, in a mixed design, you will also have multiple groups. So you have more than one group, each of which is measured repeatedly. And so you can ask, is the between groups factor different in general on the dependent variable? So regardless of, say, time of measurement, which is just an easy thing to use as your repeated measure, it would be what you use in a longitudinal design, is on average, across multiple times, there a difference between the groups? And the third question is your interaction effect. So it's the interaction between the between groups factor, and the within groups factor is the interaction between belonging to one group or another and change over time. And so that interactions are contingency effects. Is the difference between groups contingent on the repeated factor? For instance, is the effect of a group condition, experimental or control, different according to the time when it's measured with multiple time points measured? Does experimental do better than control at time 1, but not at time 2 And does it actually perform worse at time 3? That would be an interaction. If it performs better at time 1, worse at time 3, that would be an interaction. So in that case, the effect of experimental versus control condition is contingent on time of measurement. So we're going to show not the SPSS commands, but just the results of a mixed design ANOVA. Mixed designs ANOVAs are also called within and between designs. They're also called split plot designs. So what we're going to look at is data from 80 students in an experimental study of the effect of feedback source on self-efficacy when measured over multiple times. And you're going to have students who are randomly assigned to one of 2 conditions of the feedback source. That's your independent between groups variable. And we're going to say they're either getting self-feedback or peer feedback. I'm going to administer the feedback intervention daily over 3 weeks, and you're going to test them on self-efficacy. So that's your dependent variable, self-efficacy. And you're going to measure that at the end of each week, so 3 times. And this is called a nested design as opposed to fully crossed because students are nested in the condition. Half of the students are nested in the self condition and half of them are nested in the peer condition. You don't really need to worry about nested versus crossed designs, not in this course. You can also call this a nested design. So we, again, model multiple effects between subjects. And in SPSS, that's called the source, which is, I don't know why it's called the source. I guess it's the between subjects source of variability. And so we're going to be looking at the between subjects effect of self versus peer feedback. Then you have your within subjects effect. So that's time in this case, 1 week, 2 weeks, and 3 weeks. And then you have the within and between interaction. So does the difference between self and peer on self-efficacy, is that significantly different? That difference in means of self-efficacy, is it different according to time point? Is the difference between self and peer contingent on when is the measurement? And as I said before, but with the more specific example here, does it matter differently on self-efficacy that people are measured at time 1, time 2, or time 3? For instance, does self-efficacy better for students who receive peer feedback the first time of measurement, but in the second and third time of measurement, does self-feedback related to difference in self-efficacy? So time matters as well as group. So first, to look at the assumption of multivariate normality. There are tests for it in SPSS, but none of them are kind of the right test. And I'm not going to go into detail on them. Because none of them are the right test, I would not advise you to worry about them. We will look at them later, but with regression. But for now, we're just going to look at the scatter plots, which I usually use what's called this PP plot. There's another plot called the QQ plot. There's detrended plots, but I just look at the basic normal PP plot, which is the dependent variable at each time point graphed against the normal distribution. So it should be a straight line. If the distribution of self-efficacy at time 1 is normal, then it should fit with the normal distribution relatively perfectly in a straight line. So we look at these 3 lines. This is self-efficacy at time 1, self-efficacy at time 2, self-efficacy at time 3. These are small plots. They're not at a high level of resolution. You can see that in some places you have departure from the lines. There's no test of this again. If you were to put a line of best fit, you have no test of whether or not these values are different or significantly departure from the normal distribution. What you might notice is that the differences are in different places. And that's really what you're looking for. Does this matter enough? You'd have to use a test. Again, a test isn't available, and the tests may not really be, they're certainly not definitive. There's nothing definitive with the multivariate normality test. People argue about how to test this, whether to test this. So, and the tests are robust to the violations. So we're not really going to worry about that. We're going to say that these are adequate. Just bear in mind that they are adequate but not conclusive. But there's nothing truly alarming in this data. So we're going to move on to the other assumptions. First, we're going to look at the descriptives. And descriptively, the main thing that you might notice here is that you do have a consistent order between self and peer. At this case, at this time point, the first time of measurement, self performs better on self-efficacy than peer. At this time point, self performs better than peer. And at this time point, very small difference, but self performs better than peer. So that might be a significant difference. It might not. We are just working from descriptives. We certainly don't know. But looking at descriptives is always a good idea. Then we're going to go on to another multivariate test of assumptions, which is that the covariance matrices of all the dependent variables are equal across all the groups. So the extent to which self-efficacy at time 1 varies with self-efficacy time 2 is not contingent on whether you are in the self versus the feedback or the peer feedback condition. And the box plot, the box test in this case is not significant, so this test appears to be met. And most of the tests of assumptions are not conclusive, but you certainly do not want to have a significant effect because that means you have failed the test of assumptions. The idea that you've met the test because you don't have a significant effect is not really accurate, but you don't appear to have more than chance differences in the differences among the covariances between your variables. And that's going to be, so now we're going to go on to the overall multivariate test. The further assumptions will be just for within groups. So this test looks at both within and between groups simultaneously. So simultaneously, both groups, when you have variables that are associated that both contain the time and the time, even though this is the interaction effect, this contains time. So this has to do with your multiple measures, because time is involved, even though your other variable, your between groups variable, is involved. Anything that involves the multiple repeated measures is going to be tested against the multivariate test. What you'll see is that time is significant, and the other effect that involves time, which is the interaction, is not significant. So we have a significant effect according to all of these kinds of tests, all of which are F-tests. Using any of these kinds of tests, we have a significant effect for time, and we do not have a significant effect for the interaction. So this is the overall test for the within anything that involves within subjects. And there are multiple kinds of tests reported: Pillai's trace, Wilks lambda, blah, 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 blah. The test, you'll see that the in this case, the results are the same. They are not always the same. And in my experience, the most common test that is reported in the literature is Wilks lambda. But you kind of look at conventions in any journal that you're interested in. They don't tend to be different, at least in the kinds of experiences that I have with mixed design analyses. And you'll see also these multivariate tests with simple repeated measures, but of course they won't have that interaction because you don't have the between subjects source variable. This is kind of like your omnibus test. The within subjects has a assumption, and in this case, the assumption is not rejected. And we use the Mauchly's test for that. A little annotation. The Mauchly's test is not significant, so we have met the assumptions, or we have failed to reject the assumption of sphericity. These epsilon values are adjustments that you would make only if you had failed to meet the assumption. And they're adjusted within subjects effects, which I believe we'll see later. And you don't really need to worry about them because you have not rejected the assumption. You do use these if you have failed to reject the assumption. And now we will have the F-tests of the variables that include. So these are not, this is not kind of an omnibus test. This is tests for specific effects. It's not the test of the entire model. And we're going to look at, oh, sorry. We're going to look for the significance. This is your interaction, time source. Time source is your interaction. Time source is not significant. You'll see that there are multiple tests used. One is when the first one given will always be when sphericity can be assumed, and you've met the assumption of sphericity, so you're going to use this test. The other tests use this epsilon. So the epsilon in the previous slide value to adjust the degrees of freedom. And so that will change your mean square, and it will change your F If you have met the assumption, it's not going to change your F by very much. If you have failed to meet the assumption, it may change your value more. But in this case, we're just going to use sphericity assumed, and we get an F of 5.789, which is significant. Partial eta squared is 0.07. So that's the effect size. Partial eta squared cannot, or is difficult to interpret directly. So you usually will just report the magnitude of that. So change over time is significant. That's your time variable, but is not dependent on source. There's no interaction effect. And then we're going to move on to testing the between groups. So we've looked at the test of the repeated measures, which is significant, and the interaction, which says that there is no difference between peer and self contingent on the time of measurement. But let's go back to this for a second. What this tells you is that across time, regardless of group, there's a difference. Okay, so people change over time regardless of their group membership. This tells you that people's change over time is not contingent on their group measurement. And back to this one more time, if the interaction had been significant, then you couldn't really interpret the time variable, because what you're really saying is that, yeah, there's a consistent change over time, but sometimes it's related to one thing and sometimes it's related to another thing, so we can't talk generally about time. You never talk about a main effect with a significant interaction. You always have to probe that interaction. Okay, so now we're going to go into the between groups effects, and we're first going to look at Levine's assumption, which is the homogeneity of variances between the groups. So in this case, none of, even though there are multiple ways of testing this, the between groups at feedback stage 1, feedback time 1 is has a non-significant Levine's test. At feedback 2 is non-significant, and if we looked at feedback 3, it's not significant. So the error variances, the residual variances, are essentially, they are not unequal regardless of the time that people have been measured. Okay, so now we're going to look at the test of between subjects effect. We have met the assumption for between subjects, and we're going to look at the source variable, that's self versus peer, and we're going to see that that's significant. So now we've seen a main effect of time having met the assumptions, and a main effect of source having met the assumptions. And what this tells you is that on average, regardless of time point, in general, self-feedback is higher on self-efficacy than peer feedback. And how do we know the direction of that? We can just go back and look at the means. So consistently, self-feedback was higher, and that's just because we just have two groups. You can just look at the means to see where the difference is. Consistently, self-feedback is higher on self-efficacy than peer feedback. So note that that is averaged across all levels of time points. So regardless of time, self-efficacy is higher for self-feedback. And back to our within, there's always growth over time, or always change over time. Consistently change over time, consistently difference between groups. Two main effects. So Do you want to do post hocs? Post hocs tests of the linear trend is provided by default in SPSS, and you only want to do post hocs if you do not have an interaction. If you have an interaction in mixed design repeated measures, this is kind of horrible. And I really, it's very, none of the tests are really adequate as given in SPSS. If you have a priori hypotheses, it can make sense to test them one by one. If you don't have too many groups, you're not going to have to worry particularly about alpha inflation. You can always use Bonferroni. But as I said before, the profile plots may be best for you. Now we happen to know that time in general is significant. So we might want to see, is it a linear relationship? In other words, does self-efficacy consistently improve over time? Or is it kind of an up and down effect? Either might be significant if it's consistent, regardless of group, and it's likely non-chance, regardless of group. It could also be going down. But often with time, you want to see whether there's continued growth versus some kind of plateauing effect. So in this case, the linear trend is a pretty good thing to examine. And in this case, we do have a significant linear trend. In other words, there's a consistent change from time to time in self-efficacy. The F doesn't actually tell us the direction of time, so we're still going to look at the profile plots so we can make sure of the direction of time. We could also go back and look at the descriptives. But the profile plots are usually pretty explanatory. So we're now going to look at the plot of these data when we had no interaction. And we have a line for peer, which is red, peer feedback, and a blue line for self-feedback. Their dependent variable is self-efficacy measured at time 1, time 2 here, and time 3. And first of all, we'll see the main effect between groups. Regardless of time point, there is a difference between self and peers. And this means that there's an average difference between self and peers. You'll note up here, there's really not much of a difference anymore by the third week. But in general, there is a difference when averaged across time. Basically, this difference and this difference are so large that when averaged over time, this is not going to detract from the overall difference associated with self-feedback. And there is also, here's your effect for time, growth over time for both groups. So you can kind of imagine that you had put in a line that didn't account for group membership at all. It's not a very good line. It might be an adequate line. We could make the line where we just had one group if we wanted to. And regardless then of group membership, we have an consistent upward movement, okay? Average over all these groups, there's a consistency in the upward thing is your linear trend. But there is, regardless of group, there is always consistent change over time. And the linear trend tells you that it's linear. So I think that's pretty much it. As I said, if you have a significant interaction, you're probably just going to describe what you see in the box plot. It's, or you could look at specific a priori hypotheses, like the difference between, you could make difference scores, and you could say the difference between time 1 and time 2 compared between group 1 and group 2. And you have to adjust your error term. There's a lot that you have to do manually. The tests in SPSS will basically not do this. So you're going to have to go beyond what's covered in the scope of this course. But I would basically just suggest, even beyond the scope of this course, looking at the profile plots. You might want to go into, no, this is probably where I personally would stop, because the tests of significance are not fabulous for this in terms of any tests of significance that I know of for a mixed design model. Now, probably people do have answers to this, but they debate the answers to this considerably. And I think with the kinds of data sets that we tend to see in educational research, then moving to descriptives where your claims are more modest is the right way to go. So I'm pretty sure that's everything here. And let me just check that there's nothing in the further slides. Oh, we're done. So I hope you got something out of this. And it certainly is actually a really nice design for many of the sorts of things we would do in educational research. Basically, what you're looking at is between groups differences in a longitudinal design. One of the things that limits this is that you can have no missing data. So anyone who is present, say, for time 1 and time 3, but not for time 2, is rejected from the data set. And if you have a lot of people who disappear at one or another time point, so if you have 80 people who start out and then 75 people who are present for time 2, and then 65 people who are not necessarily the same people who dropped out in time 2, who drop out at time 3, you may be whittling away your cases. There are methods to impute missing data. And there's some pretty fancy methods to impute missing data, and there are different ways of analyzing these data that allow for missing data. However, I'm kind of a skeptical analyst, and I'm not really fond of imputation. It does allow you to test cases that have dropped from the data set, but there are a lot of reasons that I may talk about later in the course. Basically, you don't know why people have left. And they may have left, hey, because they really hate peer feedback, in which case that's a biasing factor. And so you need to be thoughtful, and these designs work best when you have higher control over your subjects so that you can count at least on, hopefully on getting a lot of them for all time points, which might mean getting the time points close together, and or ensuring that absence on time points is pretty random. So for instance, if it's due to simply school absence due to illness, it's fairly random, and you could either possibly impute those data or just detract that person from the data set. Their missingness is what we call missing at random. The I'm not going to go into that in any more detail, and I do hope that you will consider using this design if it suits your data, because it's a pretty powerful design and it's associated with some pretty nicely set up research questions.